Hello and welcome to our lesson on piecewise functions. So piecewise functions are precisely that. They're functions, and in fact one function, each piecewise function is one function that is composed of several pieces of other functions. So a piecewise function is one function, but it is made up of pieces of other functions, hence the name. Now, we know that when we're looking at a function, by definition, every x value can correspond with exactly one y value, or graphically what we're going to see is a graph that passes the vertical line test. If I took, for example, these two parent functions and graphed them on the same coordinate grid, there's going to be some overlap there. So if I graphed the entire v, that would be centered by about the origin there, and then I graphed my exponential that would look like this, then those two graphs together are clearly not a function. The only way for this concept to work, for a piecewise function to actually be a function, is to restrict each piece to a specific domain. So each piece of our piecewise function is restricted to a specific domain, and then if those domains don't overlap, so if, for example, we have all the x's less than 0, then all the x's greater than or equal to 0, there's no overlap there, then you won't have any overlap in your pieces, and then you should be maintaining a function. And so I graphed this as an example. If I wanted the absolute value function, again, my absolute value function is a v shape, but if I only want that for the x's less than 0, then all the x's less than 0, those would be these x's here, that's where I would want my graph, and that's exactly what we see here in red. And again, this piece is that piece of that function. Now notice this is only for x's that are less than 0, not including, and that is why at 0 you see that open circle. Now the next piece is our exponential function, but again I don't want the entire exponential function. I only want it for the x's that are greater than or equal to 0. So these, I gotta sneeze. Excuse me, I'm so sorry. For the x's greater than or equal to 0, so the exponential piece of my function, again starting at an x value of 0, would be this portion of that graph. So just that piece of it. Now notice here, these are for x's greater than or equal to 0. That means include the 0, and you'll see that closed point starting that graph. And if we put a vertical line anywhere on this graph, we're going to only pass one time. The only possible issues that will arise would be right here, and that's where overlap could happen, but because one of the domains includes 0 and the other doesn't, one is an open circle, one is closed, only one of those points is defined in the function. So if we put a vertical line there, we would only be counting the point that is closed. We would not be counting the open point, if that makes sense. Okay, so that's the concept behind a piecewise function, and hopefully we've seen these before. So we should be able to produce a graph of a piecewise function if we were asked to. This is something you could do by making a table of values. It's like the old school way to do it. I don't actually make a table of values by hand. I sort of make a table as I'm going along and making the graph at the same time, and I'll show you. So you're going to make a table of values for each piece, but you have to make sure that you're using x values, table values, right, inputs. Let's say inputs, just in case I change the variables. Well, I don't think I did, that are in the domain. So each piece that you're graphing, you could make a table of values for. You can just use your graph and make the table as you're graphing, but make sure that the inputs are in the domain for the piece that you're trying to graph, so that you're not making any overlap. And so the part that you'll have to be careful with, again, is going to be these end points. That's where we don't want any overlap. So you have to remember, if we want to include an endpoint, then we will use a closed point, and we're going to want to include endpoints when we see greater than equal to or less than equal to. And to exclude or not include the endpoint, we're going to use an open circle, an open point, and that's when we have just the greater than or the less than without the equal to. It's also helpful when we're doing this to keep in mind the parent functions. So when I know when I'm graphing each piece, the general behavior and shape of the graph. And then also, lastly, remember the graph of a function has to pass the vertical line test, so that if we did by accident create overlap in our graphs, we're going to know right away we did something wrong. Okay, so we're going to try to graph this piecewise function, and the first time you do this in college algebra, maybe you're making a table of values and writing all these things out, but we shouldn't have to do that here. we can just make the table as we graph. So the first piece is a linear piece, and I know that this line, this piece of this linear graph, is only going to be for the x values that are less than -3. So I'm going to go to -3 on my x-axis. That's going to be here. Come on, pen. These are the x values that are in that domain. So those are the x values that I want to input into that function. So I'm going to start, even though it's not included, I'm going to start at -3. If I input -3, 2 times -3 would be -6. -6 plus 1 would be -5. So at -3, -5 is where this line is going to have an endpoint, and that's going to be an open point because we are not including -3 in that domain. And then just pick another input in that domain. So pick something less than -3, something in that highlighted domain. So maybe we pick -5. 2 times -5 would be -10, and -10 plus 1 would be -9. So at -5, our graph is down here at -9. And that's really going to be enough. It's a linear function. 2 points is enough for us to graph that line. So that's what the first piece is going to look like. Second piece is a radical functions, and it's going to be shifted over, although that shift would be hard to deal with because we're only looking at a piece of it to begin with. But I know the shape of the radical function, and this is over the domain from -3 to 1. So from -3 to +1, those are the inputs I'm dealing with here. And if I have a start and a stop, like I do in this interval, then I definitely have to input that start and stop, and maybe one other point in between. So let me input the -3. When I go to input the -3, -3 plus 3 makes a 0. Square root of 0 is 0. So at -3, 0 is where this graph is going to start. And because we're including -3, we're going to start at -3, 0 with a closed point. And then I'm going to go ahead and input the other end point. So the other end of our domain, the +1. If I input 1, 1 plus 3 is 4, and the square root of 4 is 2. So at 1, 2, I'm going to have a point, and that one's going to be open because we are not including the 1. And this is just going to be a hill-shaped graph, so I'm good just connecting those in that fashion. Okay? And if you wanted to pick something else in between, you totally could, but I don't know they're going to have any nice perfect squares if you choose anything in there anyway. So endpoints should be fine. And then last piece, we're looking at, I need another color, all the x's that are greater than 1 for this reciprocal function, or our parent rational function. So for all the x's greater than 1, that means this is the domain that we're dealing with for that piece. So again, I want to start by plugging in that endpoint of our domain, the end of our domain, which is going to be 1. So when I input 1, I get 1 over 1, which is 1. So this graph is going to start at 1, 1, and this is going to start with a closed point because this domain includes the 1. And then I could pick something else, although I know the behavior of this function from here because, again, it's one of my parents. If I plug in a 2, I get a half. Plug in a 3, I get a third. And these values of my fraction, they're just going to get smaller and smaller and smaller. They're going to be approaching 0. So we'll just keep moving that direction, and there it is, a graph of our piecewise function. Now this is absolutely something we should be able to do by hand, but if we wanted to confirm our work with Desmos, or if you were just asked to make a piecewise function using technology, then Desmos does this quite nicely. You just have to know how to plug it in. So in this same exact example I put into Desmos for you and screenshot a little picture. When you're going to do this in Desmos, and you can see our picture looks basically like what we did on the paper, you're going to put each piece into its own line. So here's the first piece, here's the second piece, and then here's the third piece, each into its own line. And then after the function, you're going to have to put its domain restriction. But the important thing when you go to put the restriction in is the braces. So when you see this written on paper, sometimes you'll just have your functions, and then you'll have commas here, and then you'll have your domains. Sometimes you'll have your functions, and then you'll have the word if, and then you'll have your domains. Sometimes you you have, I don't know, all kinds of options for things that can go in here. Sometimes you don't see anything there, you just see the function and then the domain, or maybe just a space. But when you're putting it in Desmos,
You don't need to put any spaces or any commas or any words. You're just going to type the function in, and then you need to use the brace to enclose its domain right afterward. So the brace is that squiggly parenthesis, okay? So not the parenthesis, again, the brace. Those are what you have to use to enclose the domain, and you put those domains directly after each piece, and it produces the graph for you. Now, the only downside to Desmos is that it does not explicitly show you the open points. If you look at the graph that's created, they all look like they're closed points. But we know, for instance, that this one should be open, and we know also, for instance, that this one should be open. So if, like you wanted to make a really nice thorough graph in Desmos, again, you're going to type each piece in there. It's going to give you this picture. If you wanted to be clear that the point that we graphed here at, let's see, -3, this one right here, at -3, -5 was open, then you can actually show that here by typing in a coordinate at -3, comma, -5, and you'll see it plot that point there. And if you hit the little settings wrench up here and then tap on the purple circle next to that point, you have the option to make it an open point. And really you can change it to green so that everything matches. And the same thing for the other point that's up here, this one that's at 1, 2. So if I type the coordinate in here, 1, 2, and use my settings, let me change that to purple so it matches and make it an open point. And then everything is as it should be. So it doesn't explicitly give you the open circles, but you can put them in there, and you can even check the little box to make it label so that it's really clear. If you were asked to use technology, then that's sort of a process to go about doing that. Okay? So graphing a piecewise function, again, shouldn't be anything new. Just restricting each of your tables of values or your inputs to the domain that you're given. We should also be able to use a piecewise function to evaluate. So, for example, going back to our first topic for this module, if I define g of x as this linear function over this domain, this cube root function over this domain, and this quadratic function over this domain, we should be able to evaluate something like g of -5. So our input of -5, when we go to do this, we just need to make sure we're inputting into the correct function. So I have to look at the input and make sure I'm finding the right domain, and that domain tells me which function to use. So -5, we see this happening in two spots, right? -5 for an input, but it's not included here. -5 is included here. So -5 is in this domain, which means this is the function I would have to plug into. So even though there are three pieces of this function, I'm going to plug into the one that has the corresponding domain. So g of -5 would be equal to -3 times -5 minus 4. That's -15 minus 4, which would be -19. And then similarly for g of 0, so 0 is in here in between -5 and 2. So since 0 is in this domain, I would plug into this function. So the second piece, that means g of 0 is going to equal the cube root of 0 minus 1, and the cube root of -1 would just be -1. And then g of 2, so 2 occurs here, 2 occurs here, but not included in the third one. Right, this is where 2 is included, where we're equal to 2. So again, I'm going to plug into that cube root function. So this would be the cube root of not 0 minus 1 or x minus 1, but 2 minus 1. So that's the cube root of +1, which is just 1. And then g of -10. So -10 is definitely less than -5. So we're going to plug into that linear function again. So this would be -3 times -10 minus 4. That's a +30 minus 4, which would be 26. And then g of 3. So 3 is an x value that's definitely bigger than 2, so we're finally going to be plugging into that quadratic function. So this would be equal to 3 squared plus 3, and 3 squared is 9. 9 plus 3 makes that one a 12. Okay, so then we have a whole bunch of points here. If we were to actually graph this piecewise function, you would have a point at -5, -19. You'd have a point at 0, -1. You'd have a point at 2, 1. A point at -10, 26. A point at 3, 12. All right, number 7, just again to do some review of our function notation. If I said to find g of -7, it's a couple things involved. G of -7 means I gotta find g of -7 first. So -7 is an x value less than 5, so -7 is going to get plugged into our linear function. So I'm going to plug in here. -3. Let me find that piece first. So g, oops, hold on. Let me find g of -7 first. So I said plug into the linear function, and I forgot it was -3 times the -7, and then -4. That's 21 minus 4, which is going to be 17. So I found g of 7. I found that it was 17. That means this now can be replaced with 17. So to finish this problem, we're going to find g of 17. So 17 is going to go to another piece because 17 is now in this domain. So if I plug 17 into this domain, is that a -4? Yep, okay, geez, making sure I'm good. Then I have 17 squared, and then, shoot, I'm sorry for all this scrolling if that's giving you a headache, and then a +3. So 17 squared is 289, 290, 91, 92. So this is going to be 292 for the output there. Okay, so we should be able to use piecewise functions to evaluate. We should also be able to sketch a graph of a piecewise function and use technology to graph a piecewise function. And what I want to show you next are a couple of examples of piecewise functions. So one that, is an example that actually occurs in your situation as a student. You're going to see this type of behavior happen, and hopefully the piecewise function I'm going to show you makes sense. But all the piecewise functions that we're going to look on the back are what we call step functions, or sort of informally we define these step functions as piecewise constant functions with just a finite number of pieces versus infinite pieces and things that you're going to see way later on in linear algebra if you ever get there. But this is a step function, and maybe the name of this type of function makes sense. So it's piecewise. We can see pieces of functions in there, but we also call it a step function because each of these pieces looks like a step, like you could sort of take steps up a ladder here. And then a piecewise constant function here. The step function is a piecewise constant function because you can see each of those pieces is constant, it's flat, it's not increasing or decreasing. Now the particular example that I have here is your grade percentage versus your grade point. So at the end of a semester of classes, when your grades are posted, if you have an A, which is generally anything between 90 and 100, that A counts on your GPA as 4 points. B's, anything from 80 to 89, or as close to 90 as you can get, those count on your grade point average as 3s. For C's you get 2s, for D's you get 1s, and if you fail a class you get 0 points. And then all those points get divided by the number of classes you take, and that's how you get your GPA. So if you had 4 classes and you had an A and a B and a C and an A, then 4 plus 3 would be 7, plus 2 would be 9, plus 4 would be 13. That gets divided by the 4 classes you took, and that 13 divided by 4, is that what I said? Yeah, 13 divided by 4, that would be what? 3.25 for your GPA. So that's how your GPA is calculated. Each of your percentages, your grade letters, translates into a number of points. Okay, so when we are doing this when computers are calculating your GPA, any failing grade, that's any grade below 60, is not going to get you any points. So anything here from 0 points up to 60 points, percentage points, is going to earn you 0. So it doesn't matter if you got a 10% or a 59% or 59.99. If you got infinitely close there to 60, but not including the 60, because 60 would be a D, again, not getting any points, okay? Where if you earn something between 60 and a 70, not including the 70, oops, you can see that open circle there, then you're going to get 1 point. If you score a grade percentage, earn a grade percentage between 70 and 80, not including the 80, then that would be a C and you're going to get 2 points. If you score between an 80 and a 90, not including the 90, that would be a B and you're going to get 3 points. And if you score between 90 and 100, including the 90 and 100, that's an A and you're going to get 4 points. So again, this is an example, a real life example of a step function. It is a piecewise constant function. So each of the pieces, they look like steps and they are constant, they are flat. Now if I asked you to write a piecewise function to represent this, like what would I put into Desmos to make this picture? Let's call it f of x. It is made up of 1, 2, 3, 4, 5 pieces because there are 5 different grades, right? You can get an A, you can get a B, you can get a C, you can get a D, or you can get an F. And this translates the same way here. So this is your F, right? And then your D in here, and your C in here, and your B here, and your A here. I don't want to clog all this up though, but just so you're understanding, okay? So if we are our inputs, our grade percentages are between 0 and 60, then our output is going to be 0 points, okay? Now, our output is a constant 0 no matter what we are for those inputs. So our constant value of 0, again, is connected with all the inputs from 0 to 60. So we would want 0 less than or equal to x less than 60. Okay, again, we want to include the 0, and then we can't go below that, and we don't want to include the 60 because that's a D. Now, if we said if we're in the 60 to 70 range, maybe I should have made these colors correspond. It's okay. We're going to get 1 point. We're going to have a constant 1 point here, and that's if we have grades between 60 and 70. So we have D's. So we're less than or equal, or greater than or equal, it's less than or equal, but x is greater than or equal to 60. 60 is less than or equal to x, and then less than 70. So those are D's. And then we're going to get 2 points if we have a C. So that's going to be from 70 to 80, not including 80. And then we're going to get 3 points if it's a B. So that's going to be 80 to 90, not including 90. And then we're going to get 4 points if we have an A. So from 90 to 100, and we can include the 90 and 100. Okay, so those are just constant outputs for those particular inputs. So again, that's a step function, but it's a piecewise constant function, sort of informally by definition. Now, some other step functions that are something I want to introduce you, just so you're not seeing them for the first time when you go on to calculus, are what we call the floor and ceiling functions. So the floor function is where we'll start here. Again, this is a step function. It's also known as the greatest integer function. And basically what it does, it's a hard one to say, but it takes a real number. Any real number input is going to be possible here. So it takes any real number input, x, and its output is the greatest integer that is less than or equal to x. Now that sounds probably really complicated, and it does to me too, but here's the gist of the idea. Any real number input is rounded down to the nearest integer to get the output. So, for example, and don't write this just so you can understand. Okay, let's say we're looking at a number line. Here's let's just go positive for now. Here's 2 here, here's 3 here. If I said, what is the floor for like 2.15, that if 2.15 was my input and I wanted to find the floor for that input, I want to round down to the nearest integer. So the nearest integer below it, less than or equal to it, right? That's what we're saying here, would be 2. So the floor for 2.15 would be 2. And then the ceiling, when we get to that, is just the opposite. It's rounding up, so the ceiling for 2.15 would be 3. And it's going to be that same floor for any number in there. So even if we're over here, let's say that this was like 2.99, we're always going to round down to the nearest integer. So 2.99, the floor for 2.99 would still be 2. Okay? And this works on the negative end as well. So let's say we were looking at negative numbers on our number line. Like if we were looking at, let's say negative 4 is over here and negative 3 is over here, and this would be like negative 3.5. If I said what's the floor for negative 3.5, we're going to go to the nearest integer below it, which would be negative 4. Okay? Now what if I asked you for the floor for negative 3? Well, negative 3 is at negative 3, so we don't have to round, it's already there. So the floor for negative 3 would be negative 3. Okay? So as a function, here's the notation, here's how it looks. We define this as an equation, or the equation form as f of x equals x around this. So that's the floor of x. So we have these, they look like incomplete brackets, but the ceiling function, once you see it, you'll hopefully appreciate why the brackets are this way. So I like the missing part of the bracket is that top part, right? We have the bottom part, which is reminding me to round down. That is what we're doing with our floor function or our greatest integer function. In word form, and if you do any kind of coding, you'll see this. We just call this the floor of x. And how does the graph look? Okay, well, let's, again, think about some outputs here. These are my inputs, okay? So I'm going to deal with these inputs and then graph the outputs. Instead of writing the table of values, we should be able to do this. So at negative 2, if that's my input, my output is the nearest integer less than or equal to, so my floor would be negative 2. And that's going to be a closed point there, just a normal point. If my, and this is negative 1 here on the axis. This is positive 1, and this is positive 1, and this is negative 1. Okay, sorry, it skipped. And so anything in between negative 1 and negative 2, like if I wanted to input negative 1.5, again, I would still round down to negative 2 as my output. If I took negative 1.75, my output would be the closest integer, so it'd still be negative 2. So anything that's going to be in here is going to round down to negative 2. As close as we can get to negative 1, but negative 1, when I go to find the floor for negative 1, would actually be negative 1. So I want to get as close to negative 1 as possible here for all the numbers in between, but I don't want to include the negative 1 because the floor for negative 1 would be negative 1. And then the same thing is going to happen here. Any of these numbers, these inputs in here, they're going to round down to negative 1. So we're going to have another step here, but I don't want to include 0 because 0's floor would be 0. And now anything in here would round to 0 except for 1. So we're going to get as close to 1 as possible, but the floor for 1 would be 1. And then everything in here would round down to 1, as close as we can get to 2, but not 2, because the floor for 2 is 2. And the same thing continues all the way up and down. So we have these steps, and this is what our greatest integer function, our floor function, this is what the graph is going to look like, or a piece of the piecewise function looks like. Now up here I specified this was a finite number of pieces. This technically goes on forever, but still called a step function. Ceiling function is very similar, like the floor function, a step function, but instead of rounding down, we round up. So it takes any real number input x as, again, x as input, and it makes the output the least integer greater than or equal to x, which it's so hard to wrap my brain around that. In essence, every real number input is rounded up to the least integer that is greater than or equal to that input. And here's our equation. So it looks again like an unfinished bracket. What? No, let me write that again. Looks like this. Again, oh, my pen is being silly. Maybe it's me, it's operator error. So these look like unfinished brackets, but notice the top isn't finished on the floor. So the piece that is on the bracket, the floor telling me to round down here, the piece that's on the bracket is above, that's telling me to round up. So this is kind of how I remember what to do. In word form, again, if you do any coding in word form, we could say this as the ceil for ceiling of x. And then the graph looks very similar to the graph that we just did. So again, let's talk about these as the inputs and what happens when I go to find my output. So at -2, I don't have to round. -2 floor or ceiling would be -2. Okay, but if I go to, let's say again, shoot, let me fix my axes. -1, +1, +1, -1. If I go to, let's say, -1.5 for my input here, instead of rounding down to -2, -1.5 is going to now round up to -1. So -1.5 is my input, -1 is going to be my output. And -1 obviously is going to be -1 as an output. And anything here like -1.25 is going to be rounded up to -1. And everything, let's see, -1.75 is going to be rounded up to -1. And as close as we can get to 2, right, but not including -2, not including -2 because -2 rounded is -2. So this time, the open point is going to be the start there, okay? So -1 doesn't have to round, -1 is -1. But if we are looking at, let's say, -0.75 here, then that's going to round up to 0. And this would round to 0, and 0 would round to 0. Now, -1, we've already captured that down there, but all of these things in here would round up to 0, okay? And then all of these, so I 1, I just lost where I was. Goodness. Okay, and this graph down here, I didn't finish this side over here, but like -2.1 would round to 2, and so this would continue this way. It just gets cut off. But on the other side over here, I don't have to... Oh, I'm sorry, my pen, it's like frozen. Okay, there we go. I think it's back. Alright, so I don't have to round 1, right? My output for my input of 1 would be 1. If I rounded 0.75, it would go up to 1. If I rounded 0.5, it would go up to 1. If I rounded 0.25, it's going to round up to 1. Now, 0 as my input, right? We've already captured that down there, so all of these points, all these numbers are going to round up to 1. And then same thing here. We'd have an open circle here because my input of 1, I've already captured that here. And then all of these numbers are going to round up to 2, including 2. And so basically the same thing, well, very similar to what we saw here. We're just starting with open points and ending with close, versus over here we start with close and end with open. But it's all about rounding. So the floor ceiling rounds any number down to the nearest integer unless we're already at that integer, and then the ceiling rounds up. Okay, so if you see this notation later or you see these step functions, this is how they connect. All right, and I think that's going to be enough for this particular lesson. So if you have any questions, by all means reach out. Until next time, take care.